So our motivating factor from what we just found from the ice is that we'd like to find a way to take some matrix E and multiply it by a vector and have that be the same thing as just some scalar. I call that scalar lambda. In other words, what we'd like to do is be able to have it so that if we took and kind of brought everything to one side, this would mean that E times the vector minus lambda times the vector would equal to 0. And what we can do is we can use the identity matrix to help kind of factor this out a little bit. And this would give us the equation that E minus lambda times the identity matrix times the vector equals 0. So notice that this is a homogeneous equation. So we know that there's some sort of solution to this, either the trivial unique solution of all zeros or infinitely many solutions. Now what we know because of the invertible matrix theorem is that this equation is going to have a non-zero solution so long as the determinant of this matrix equals 0. So if we have the 0, then we have some non-zero solution to it. So what we'd like to do is we'd like to then figure out what those solutions look like, what those vectors are going to be that satisfy this property of being the matrix times the vector equals some number times that vector. And there's going to be just some collection of vectors that we get from that. So let's get into some formal definitions then for eigenvalues and eigenvectors. So let V be a vector space. Given a linear operator or transformation going from that vector space to itself with a corresponding square matrix and a non-zero vector V, if L times V equals lambda times V for some scalar lambda, then we say V is an eigenvector of L with eigenvalue lambda. And so our process for trying to find these eigenvalues and eigenvectors is to start off by finding the eigenvalues by determining and solving the equation the matrix minus lambda times the identity equals 0. And then once we have those scalars, we should be able to use them to try to figure out what the eigenvectors are. Just a little bit of definition time. So this is our main process. We're going to call the equation determinant of L minus lambda I equals 0 the characteristic equation, and the left side of this determinant of L minus lambda I is going to be the characteristic polynomial of the matrix L. Alright, so let's go through an example where we just find the eigenvalues. So we're going to go ahead and solve. Our goal is to solve for the matrix times a vector equals lambda times some vector. And that's going to work for a specific value and a specific set of vectors. So what we'll do is we'll start off with the determinant of the matrix minus lambda times the identity, which we'll set equal to 0. So we will take the determinant then of 5, negative 3, 6, negative 4, minus lambda 0, 0, lambda. So because we have a 2 by 2 matrix, we'll use the 2 by 2 identity to work with. And so we're trying to find then the determinant of 5 minus lambda, negative 3, 6, and negative 4 minus lambda, which we'd like to be equal to 0. So that means that finding the determinant, since the 2 by 2 will be this times this minus this times this. So we'll have 5 minus lambda times negative 4 minus lambda minus negative 3 times 6 equals 0. So then combining that, we get, and we want to FOIL this out, so we should get negative 20 minus 5 lambda plus 4 lambda plus lambda squared plus 18 equals 0. Combining like terms and reordering things a little bit, we should get lambda squared minus lambda minus 2 equals 0. And then in order to solve this, what we want to go ahead and do is factor. So we should get lambda minus 2 and lambda plus 1 equals 0. And this tells us that our eigenvalues are lambda equals 2 and lambda equals negative 1. So these are the eigenvalues for our matrix M. Now, just because we have our eigenvalues doesn't mean that we can take any particular vector in the universe and multiply it by the matrix and get some number, or to get that matrix times one of these two numbers. What we need to do is we need to figure out what these specific vectors are that'll get us there. So let's go ahead and do that. So in order to figure out which eigenvectors are associated with those eigenvalues that we just found, so negative 1 and 2, what we're going to be looking at is trying to find vectors v such that m times v equals lambda times v for one of our lambdas. So what we're really saying is we want to figure out what vector has it so that our matrix minus lambda times the identity times that vector equals 0. So we want the set of vectors which satisfy this equation equals 0. Well, that's the null space of the matrix minus lambda times the identity. So this is the thing we'd like to find for both of our eigenvectors, or eigenvalues. So we want to figure out what those vectors are going to be. Now remember, the null space, provided it's not trivial, is going to be the span of some vectors. So it's not just one vector, it's any multiple of one, or in some cases more, vectors. So for lambda equals negative 1, we want to find the null space associated with m minus negative 1 times the identity. So this is going to be the null space of 5, negative 3, 6, negative 4. We take negative times negative, it's going to be positive, plus 1, 0, 0, 1, which will be the null space of 5 plus 1 is 6, negative 3, 6, negative 4 plus 1 is negative 3. And in order to find the null space, remember what we're doing is we're taking 6, negative 3, 0, 6, negative 3, 0, finding its reduced row echelon form, which will be 2, negative 1, 0, 0, 0, 0. Or at least it could be that we have a 1 here instead and a negative a half, but it's a little messier to work with. So this tells us that 2x minus y equals 0, or in other words, we can solve for x and we get that x equals y over 2. So then taking this back over here, the null space is going to be the set of all inputs x, y, such that x equals y over 2. So then we have the set of all y over 2y, such that y is an element of the real numbers, which is just the span of 1/2 and 1. Which we can think of as being the span, if it makes our lives a little easier, of 1, 2. So remember, since we have the span, we're really looking at any multiples of these vectors. So it's not just 1, 2, it also could be 2, 4, negative 1, negative 2, 100, 200, so on and so forth. And so this is going to be our eigenvectors associated with -1. If we want to go ahead and look at the eigenvectors associated with 2, what we'll do is we'll find the null space for our matrix minus 2 times the identity. So this will be the null space for 5, -3, 6, -4, minus 2, 0, 0, 2. Be careful and make sure you're distributing that minus through both of these. What we should end up getting is the null space for 3, -3, 6, -6. And if we went ahead and did this over on the side, we took this matrix, got its reduced row echelon form, what we'd find is that we had 1, -1, 0, 0, 0, 0. So we want, that tells us then that we want our constraint to be x equals y. And so what we have is the set of all x, y, such that x equals y, which is going to be the span of 1, 1. So we go ahead and replace the x with the y, so it would be the set of all y, y, such that y, such that y is an element of the reals, and then that's how we get the span of 1, 1. So given an eigenvalue lambda for a matrix, we sometimes call the null space of A minus lambda I the eigenspace corresponding to that lambda, and a basis for the eigenspace is called an eigenbasis. We're going to get real Marvel Cinematic Universe here. I promise we don't just put the word eigen in front of everything like they do quantum. If you haven't seen any Marvel movies, I think you're missing out, but that's just personal preference. Alright, so then if we wanted to say what the eigenspace was for lambda equals 2 for this matrix, we'd say that the eigenspace associated with the eigenvalue for 2, this is how we would denote it, equals the span of 1, 1. And then to kind of continue the example, if we wanted to say the eigenspace associated with -1, we could say that it was the span of 1, 2. So what did we just show? We just showed that if we took the matrix times the vector 1, 2, then that would be the same as taking 1, 2 times -1. Or if we took the matrix times 1, 1, that would be the same as taking 1, 1 times 2. Alright, so let's go ahead and do another couple examples. So let's start with trying to find the eigenvalues for this matrix. So we're just finding the eigenvalues. We're looking at the determinant of m minus lambda I, setting it equal to 0. So it's a 3 by 3 now. So we have the determinant of 5, 1, 3, 0, 0, 1, 0, 0, 1, minus lambda times the identity, so it would be lambdas on the main diagonal, zeros everywhere else, and we want it to be equal to 0, and so we have that we would like the determinant, I'll kind of combine the notation here, of 5 minus lambda, 1, 3, 0, 0 minus lambda, 1, 0, 0, 1 minus lambda. We want to set that equal to 0. Now what you might remember is that if we have a matrix that is upper triangular, so below the main diagonal is all zeros, all we need to do is multiply by along the main diagonal in order to get our determinant. So we should get 5 minus lambda, 0 minus lambda, and 1 minus lambda equals 0, which means that our eigenvalues are going to be 5, 0, and 1. So that kind of leads us to a nice theorem that says the eigenvalues of a triangular or diagonal matrix are just going to be the entries along the main diagonal. So if you notice, our eigenvalues were 5, 0, and 1, and our main diagonal entries were 5, 0, and 1. All right, so that's pretty neat. There's a nice little proof here if you wanted to go ahead and read through that. And we also have a nice little lemma here that says that if 0 is an eigenvalue of a matrix A, then that matrix is not invertible. And this comes a little bit from using our invertible matrix theorem. So if 0 is an eigenvalue of the matrix, then for lambda equals 0, 0 equals the determinant of A minus lambda I, which means it's equal to the determinant of A minus 0, which is just the determinant of A. And that means then that the determinant of A is 0. So if the determinant of A is 0, then by the invertible matrix theorem, it's not an invertible matrix. All right, so let's go ahead and find one of these eigenspaces, eigenbases. So let's go ahead and look at finding the eigenbasis for the eigenspace associated with the eigenvalue of 0 for this matrix. So we're trying to find E0, which is going to be the null space of m minus 0 times the identity. So we'll write it as a span, and then we'll verify that we have a basis. So the null space for m minus 0 times the identity is just going to be the null space for the matrix. So if we wanted to find the null space for the matrix, we'll go ahead and take 5, 1, 3, 0, 0, 1, 0, 0, 1, augmented with zeros, get its reduced row echelon form. And what we'll find is that we have 5, 1, 0, 0, 0, 1, 0, 0, 0 on the left, and on the right we still have all zeros. So some equations this gives us then. Here, because we don't have any leading terms here, this is a free variable. And so what we get is 5x plus y equals 0, and z equals 0. Y is our free variable, so we can rewrite this to be x equals negative y over 5. And then when we go ahead and start writing this null space, have the set of all x, y, z such that x equals negative y over 5 and z equals 0. And so this will become the set of all negative y over 5, y 0, such that y is an element of the real numbers. And this tells us then that our eigenspace for the eigenvector 0 will be the span of negative 1/5, 1, 0. Which is one of many ways we can go ahead and write that. So now we have this eigenspace. So this is a spanning set. We want to know if it's linearly independent. So spans linear independence. And since we have a single single non-zero vector, say that 5 times fast. I can't apparently. We have something that will be linearly independent because this times a scalar equals 0 only works if that scalar is 0. So linearly independent, yes. So that means that the eigenbasis for lambda equals 0 is just going to be the set containing this vector -1/5, 1, 0. Alright, so in the next video, what you'll be doing is you'll be trying to play around with this idea of computing eigenvalues and their eigenspaces for two matrices. So for the best results, I'd suggest looking at ICE 9, trying to find these eigenvalues and eigenspaces for problems 1 and 2 on your own, and then going ahead and clicking and watching the video.